our experience with radicals has been, if we take the square root of a perfect square, we get a whole number. The reasoning is that 5 squared is 25, and squaring and square rooting are inverse operations. They undo each other. In other words, if we have a number like 5 squared, and then we have the square root, the square and the square root kind of cancel each other out, just leaving us with what's underneath. We're going to start digging deeper into radicals, including what happens when negatives are involved. Negatives get tricky when talking about square roots because it is true that 5 times 5, or 5 squared, is 25. But it's also true that -5 times -5, or -5 in parentheses squared, is positive 25. Both of these are positive 25, which means not only is 5 a square root of 25, but -5 is also a square root of 25. Now, it's been standard practice that when we see the square root symbol without anything in front, that this refers to the positive square root. But when we're solving equations that have radicals in them, we have to capture every possibility. If we have a negative out front of the radical, or the opposite of, this is what's used to indicate, hey, give us the negative square root. So together, the positive and the negative, we use the plus or minus notation. So to cover all square roots, the positive and negative, we have plus or minus. So when we're solving, we're going to end up using this plus or minus notation, and we're not going to have to worry about solving for a little bit. But when we're evaluating, if there's no negative, no opposite sign in front of the radical, then we only want the positive. If we want the negative, there will be a negative, an opposite sign out front of the radical. Now, this brings up another issue. I said, hey, the square root and the square cancel each other out. That's why the square root of 5 squared, the square root of 25, is 5. Well, wouldn't that mean that the square root of -5 squared would be -5? No. Because There's no opposite in front of this symbol. So what does this have to be? It has to be 5, not -5. So this requires us to have a rule. What sort of thing leaves 5 as 5, but turns -5 into +5? It wouldn't be the opposite. It'd be the absolute value. So in general, if we have the square root of x squared, the answer is actually dependent well, hold on. That's a more complicated definition. I'm going to get into that in a minute. For now, let's just say if we have a square root of x squared, the answer is actually the absolute value of x. And that definition makes this work. Oh, excuse me. Here, the square root of 5 squared would be the absolute value of 5. That's 5. Here, the square root of -5 squared would be the absolute value of -5. That's also 5. This is actually needed for any even exponent and even root, because we don't just have square roots, we also have cube roots, we have fourth roots, and they work the same way. So for all even ones, all nth roots of x to the n, where n is even, it's going to be the absolute value of x. What about odd roots? I wouldn't be drawing attention to this only being when n is even if something different didn't happen when n was odd. So let's take a look at some cube roots and see what we can figure out. The cube root of 8, well, that would be the cube root of 2 cubed. And the cube root of 8 is 2, because the cube root and the cube cancel each other out. Two times 2 times 2 is 8. Well, what is the cube root in parentheses of -2 cubed? We'd be looking for the cube root of what number? Well, when we were dealing with the squares and the square roots, it was the same number. But -2 times -2 times -2 is actually -8. We can take the cube roots of negative numbers. So the cube root of a negative number is actually that negative number. So that original rule that we started with, that the root and the exponent, if they're the same, they cancel each other out and just leave us with what's underneath. We don't need any absolute value for that. The nth root of x to the n, if n is odd, is just what's underneath. They do truly cancel each other out. So if we're talking about even roots, we want the absolute value. If we're talking odd roots, then we don't want the absolute value. And this is fun because we're going to do some examples with this. And then I'm going to basically say there's these magic directions. And when you have this as a direction, you don't have to worry about the absolute value bar anyway. But first, we need to understand the rule before we can see why it's okay to throw it out sometimes, given a specific direction. So let's look at some examples. Even if I just confused you, these examples are going to make you go, oh, okay, I see exactly what you mean. Let's take a look at the cube root of negative 12 cubed. Well, a cube root and a cube cancel each other out. Since it's an odd root, an odd exponent, we're just left with exactly what's underneath. That's it. Let's look at another. The fourth root of negative 3 to the fourth. Well, a fourth root and a fourth power cancel each other out. Since it's even, an even root, an even power, we have the absolute value of what's underneath. And the absolute value of negative 3 is positive 3. Let's look at some more. A sixth root of negative 8 to the sixth. Well, a sixth root and a sixth power cancel each other out. It's even. So we want the absolute value of what we're left with, the absolute value of negative 8, which is positive 8. The fifth root of negative 1 to the fifth. Fifth root, fifth power, cancel each other out. It's odd, so we just have what we're left with, negative 1. Okay, let's make this interesting. the square root of a plus b in parentheses squared. Well, follow the same rule. The square root and the square cancel each other out. It's even, which means we have the absolute value of what we're left with when the square root and the square cancel away. So the absolute value of a plus b. Another just like this. The square root of, in parentheses, 2x plus 1 squared. The square root and the square cancel each other out. It's even. So we have the absolute value of what's left, 2x plus 1. The absolute value of 2x plus 1 would be the answer here. Okay, let's make this more interesting. What's different about this? Well, every other one that I've done, I've had the same root and the same power. They have to be the same root and the same power to cancel away. So we have to ask ourselves, is there a way to make this have the same root and the same power? Since it's a fourth root, can we write x to the 8th as something to the 4th power? And we absolutely can. X squared to the 4th is x to the 8th. So now, when the 4th root and the 4th power cancel each other out, and they are even, we take the absolute value of what's left, the absolute value of x squared. But something funny happens on the way to our final answer. We need to think about this. The absolute value of x squared. Is this simplified? What happens to a number when we square it? It becomes positive. A positive squared is positive. A negative squared is positive. The lowest this can be is 0. Because if the negatives squared become positive, 0 squared becoming 0, that's the lowest we can go. Well, that's the same for an absolute value. An absolute value can't be negative. It's either 0 or positive. So actually, the absolute value of x squared would be x squared itself, because x squared is guaranteed to be 0 or positive. There's no use adding absolute values, because the point of the absolute value is if we have a negative, we want to bring it positive. They are unnecessary when we are assuming that we have positive. Let's do another like this. The square root of x to the 12th. Well, a square root and a 12th power can't cancel out, but a square root and a square root and a second power, they will cancel out. X to the 12th as something squared would have to be x to the 6th squared, because when we multiply the exponents, power to a power, we get x to the 12th. Since it's even, we do absolute value of what's left, x to the 6th. But since this x to an even power is guaranteed to be positive or 0, the absolute value is unnecessary, and our answer is just x to the 6th. The reason we don't need the absolute value is because we are assuming, or we're not assuming, we're guaranteed that what is inside is a positive real number. So I said there'd be this magical direction that when we see it means we don't have to worry about absolute value anymore. And we just stumbled upon what that is. If we're told assume that x is a positive real number, then we do not need the absolute value signs. They are unnecessary. But without this direction, we need to account for things. So when we cancel those even powers, we put absolute values in. And from here on, we are going to assume that x is a positive real number. When we have a to the 1 over n, this means that we want the nth roots of a. Nth root. What do I mean by that? Well, when we have 36 to the 1/2, this is the second root of 36, square root of 36. 36 to the 1/2 is positive 6. 1/2 power is always positive root. If we wanted the negative root, then like in example B, we'll have a negative in front. So this is negative square root of 100, which is negative 10. C, negative 225 to the 1/2 is the negative square root of 225. Pretty sure that's 15. Use my math brain. Yep. Since we have the negative, it's negative 15. You are allowed to use a calculator in this class. You are encouraged to use a calculator in this class. This would be the fourth root of 625. And with the help of a calculator, we get that that is 5. E, negative 1296 in parentheses to the 1/4. This one, no solution, not possible, undefined. We will not get an answer here because we're trying to take the 4th root of a negative number. We can't take even roots of negative numbers because there are no two numbers that are the same that when you multiply them together will give you negative. Positive times positive is positive. Negative times negative is positive. So if we're multiplying something together 4 times, it's always going to be positive, no matter what. Never going to get the negative. Now F is different. It's written without the parentheses. So this is negative 4th root of 1296. This one we can do. And again, a calculator tells us that the 4th root of 1296 is 6. So this is negative 6. G. In G, the parentheses are back. The negative is inside the parentheses, but we can do it this time because it's an odd root. This is the cube root of negative 27, which is negative 3. Negative 3 times negative 3 is positive 9 times negative 3 gives us negative 27. H. No parentheses, but it's an odd root, so the parentheses wouldn't matter. We'd just get negative either way. But this is negative 5th root of 32, which gives us negative 2. So 1 over a number, 1 over a number is that root. We're going to expand this to look at a to the m over n. Here, the m is power, the n is still root. And we can look at this 2 ways. Either as a to the m raised to the 1 over n, in other words, the nth root of a to the m. But we can also look at this as the nth root of a raised to the m. But in radical form, power over root. So the nth root of a to the m. Or the nth root of a, all raised to the m. Same thing. Sometimes one will be nicer for us than the other. So in example 5a, we have 125 to the 2/3. We can think of this as the cube root of 125 squared. The cube root of 125 is 5. 5 squared is 25. Now I did it this way because 125 is already pretty big. I could have also tried to do 125 squared and then taken the cube root of that. 125 squared is going to be huge. Why not make it smaller first? Take the root first and then square. B. We have 32 to the 7/5. If we split this up, this is 32 to the 1/5, all raised to the 7th, which is 2 to the 7th. And 2 to the 7th is 128. C, negative 81 to the 3/2. The negative, since this is not in parentheses, is just going to carry into our final answer. So whenever we're done, it's going to be negative. This is 81 to the 1/2 cubed. 81 to the 9/2, or 81 to the 1/2 is 9. Square root of 81 is 9. And 9 cubed is 729. So negative 729. D, negative 27 to the 2/3. Parentheses are included here. This is negative 27 to the 1/3 squared. Negative 27 to the 1/3. The cube root of negative 27 is negative 3. Negative 3 squared is positive 9. And it would end up positive either way. If we squared negative 27, it'd be a positive number. The cube root of that number, 9. E, 16 to the negative 3/4. So we have a negative power here. How do we take care of that? Well, that's 1 over 16 to the positive 3/4. So 1 over, this would be 16 to the 1/4 cubed. The 4th root of 16 is 2. 2 cubed is 8. So 1/8. The negative exponent does not mean negative numbers, it means fractions. F. Negative 4 to the 5/2. This means they're trying to make us take an entire negative number and take the square root of it and then raise that to the 5th power. But you can't take the square root of a negative number, so no solution. Either way, if you took negative 4 and raised it to the 5th, you'd have some negative number. Can't take the square root of a negative number, no solution. So, let's look at these exponent rules one last time. Because we're about to use them with fractions. So we want to be real sure we know what we're doing before we add on the additional layer of working with fractions. So a to the r times a to the s multiplying with the same base, add the exponents. A to the r plus s. A to the r over a to the s. Top minus bottom. A to the r minus s. Negative exponent. A to the negative r. That's 1 over a to the positive r. A to the r raised to the s. Multiply the exponents together. A to the rs. Also be aware that if there's two factors inside, remember, a times b raised to the r, we give it to both. That's just for multiplication. You can't do that if it was a plus b. It wouldn't be a to the r plus b to the r. This is just for multiplication inside. And the last form of the power rule is the one that involves the fraction. A over b to the r. Give the r to top and bottom. Okay, 6a. 27 to the 1/3 times 27 to the 5/3 all over 27 to the 3rd. Same base, multiplying, so we add the exponents. This would be 27 1/3 plus 5/3 is 6/3 over 27 to the 3rd. 6 over 3 is 2, so this is 27 squared over 27 cubed, which is 27 to the negative 1, or 1 over 27. Two ways to get that. You can go, oh, there's one more factor of 27 on the bottom than on the top, so the top cancels out completely, leaving a 1, and we have 127 on the bottom. Or the quotient rule. 27 to the 2 minus 3 is 27 to the negative 1. We cannot have negative exponents in our answer, so 1 over 27. Let's take a look at B. (81 to the 5/4) times 4 to the negative 3/2. Well, you could just evaluate both. We have the 4th root of 81 raised to the 5th times negative 3/2 power, so 1 over 4 to the 3/2 square root of 4 cubed. The 4th root of 81 is 3, so this is 3 to the 5th times 1 over, this is 2 cubed, so 3 to the 5th over 2 cubed, and 3 to the 5th power is 243. 2 cubed is 8. So 243 over 8. C. Six y to the 2/3 times 2y to the 1/2. First of all, 6 times 2 is 12. Then we would have y to the 2/3 times y to the 1/2. We need to add those exponents. In order to add fractions, we would need a common denominator. That's going to be 6. So this is y to the 4/6 times y to the 3/6, which is 12y to the 7/6. D. Three m to the 5/6 over y to the 3/4 all squared. Eight y cubed over m to the 6th, and this is all to the 2/3. Okay. So for this one, we're going to square all of these, and we're going to give the 2/3 power to all of these. So 3 squared m to the 5/6 squared y to the 3/4 squared times 8 to the 2/3 y cubed to the 2/3 m to the 6th to the 2/3. So we squared all the factors of the first. We 2/3 did all the factors, power to all the factors on the second one. And now we'll simplify this. Three squared is 9. Power raised to a power we multiply. So m to the 10/6 over power to a power, 3/4 times 2. So y to the 6/4 times 8 to the 2/3. That's the cube root of 8 squared. 8 to the 1/3 all squared, which is 2 squared, which is 4. Y cubed to the 2/3, multiply, that's y to the 6/3 over m to the 12/3. 6 times 2/3 is 12/3. Let's simplify these a bit. M to the 10/3, or sorry, 10/6, that reduces to 5/3. 6 over 4 reduces to 3/2. 6 over 3 is 2. 12 over 3 is 4. We're multiplying, so this can all just come together. 9 times 4 is 36. M to the 5/3 y squared over m to the 4th y to the 3/2. So using the power rule, we have 36 m to the 5/3 minus 4, top minus bottom, y to the 2 minus 3/2. We need a common denominator to do this subtraction. 5/3 minus 12/3. 4/2 minus 3/2. So 36, 5/3 minus 12/3 gives us m to the negative 7/3. Y to the 4/2 minus 3/2 is 1/2. So finally, the 36 and the y to the 1/2 stay on top. The m moves to the bottom. It's the positive 7/3. M to the 2/3 times m to the 7/3 plus 2m to the 1/3. So we're going to use the distributive property. We're going to multiply that times that, and then that times that. M to the 2/3 times m to the 7/3. Add the exponents, we get m to the 9/3. Here we get 2m to the 3/3. Again, adding the exponents. 2/3 plus 1/3 is 3/3. So this leaves us with m cubed plus 2m. We're going to factor expressions that have negative exponents. Remember, the rule for factoring out a greatest common factor, say, when we had 4x cubed minus 2x squared, was that we looked for the lowest power and factored it out. We're still going to look for the lowest power. We're still going to look for the lowest power and factor that out. But with negative numbers, the most negative is the lowest power. So let's take a look at 12x to the negative 2 minus 8x to the negative 3. Here, don't be confused. The lowest power is the negative third. So we can take out a 4. We can take out an x. That x has to be to the negative third. Why? Because to build it up, when we think about the distributive property, we need to add something to the negative 3 to give us negative 2. Here, this is going to be 3x. 4 times 3 is 12. X to the negative 1 times x to the positive 1 gives us negative 2. Negative 3 plus 1 is negative 2. Minus 2. 4 times negative 2 is negative 8. We already have the x to the negative 3. If you need help, get tutoring. This is a review. For m to the 1/2 plus 3m to the 3/2. The lowest power is 1/2. We can factor out m to the 1/2. Times 4 gives us the first term. Times 3m to some power gives us the 3/2 power. 1/2 times how many halves is 3/2? 2/2. 1/2 times 2/2 is 3/2. But 2/2, that's just 1. Example 7c. Y minus 2 to the negative 1/3 plus y minus 2 to the 2/3. We want to factor out the greatest common factor, which means factoring out the least exponent. Here that's going to be a y minus 2 to the negative 1/3. Times 1 gives us the first term. Negative 1/3 plus 3/3 is what gives us 2/3. But 3/3 is just 1. So in the end, we have y minus 2 to the negative 1/3 times 1 plus y minus 2. 1 minus 2 is negative 1 plus y. Or if you want to write that y minus 1, you can. Negative 16 to the 3/4. There's no parentheses, which means the negative's not involved with the radical. So that would be negative on the outside, 16 to the 1/4 cubed, or negative 4th root of 16 cubed. Again, I put these parentheses in to keep the negative out of it. 4th root of 16 is 2. 2 cubed is 8, so our answer is negative 8. X to the 5/6. See how long these ones have been so far? We're throwing this one in to show you that once this becomes real algebra, once we just have variables, things become a lot quicker. 6th root of x raised to the 5th power. Nothing else we can do there. Because we don't know what x is, we can't actually go further. 3x to the 2/3. We're going to keep that 3 out of it. The base is only x. Power over root, 2/3. Nothing more we can do there. F, 2p to the 1/2. Again, we got to keep the 2 out of it. This is just the square root of p. 1/2 power square root. G, 3a plus b to the 1/4. Don't try to give that 1/4 to everything. That plus in the middle That locks us out of being able to do that. We can only give the 1/4 to everything inside parentheses when it's all factors, when it's all multiplied. 1/4 is 4th root. That's all we can do. 4th root of 3a plus b. Notice how much quicker they went once we took the numbers out of play. Once we started taking roots of variables. In this lesson, we're going to learn all the rules of roots of variables. Example 3. We're going to go backwards to exponential form again, this time with these variable expressions, excuse me. Again, equations have equal signs. These do not. These are just expressions. 4th root of x to the 5th would be x to the power over root x to the 5/4. Square root of 3y our base to the 1/2 power. Ten times the 5th root of z squared, z to the power over root 10z to the 2/5. 5 times the cube root of 2x to the 4th to the 7th. So this would be 5 times something to the something 3rd power. Our base there is 2x to the 4th. Power of that base was 7. 5 times 2x to the 4th to the 7/3. E. Radical p squared plus q. That is the square root of p squared plus q. This is p squared plus q to the 1/2 power. So we have the 6th root of 3 squared. We write this power over root. We simplify the fraction, which shows us that this is the cube root of 3. B, 6th root of x to the 12th y cubed. Power over root. That's x squared. Y to the 1/2. X squared square root of y. And C, the 9th root of the square root of 6 to the 3rd. Let's do these one at a time. That would be the 9th root of 6 to the power over root 3/2, which would then be 6 to the 3/2 to the power over root 1/9. Multiply the exponents. This is 6 to the 3/18, which is 6 to the 1/6. Or the 6th root of 6. That wasn't so bad, was it?